This is an axial flux motor, a YASA axial flux motor. It's an ultra-high performance electric vehicle motor capable of taking you further and faster due to its unmatched weight, size and power density compared to current electric cars on the road. And it's a reality today. The future of more efficient electric vehicle proposition for Mercedes-Benz AMG. This is our story, and it starts in 2005.
2005 feels like a long time ago now. It's approaching 20 years, and yet an awful lot has changed in that time, and we forget that. In 2005, we just had the Kyoto Protocol ratified, which for the first time committed industrialized nations to reducing their greenhouse gas emissions. Now, it was an interesting time technologically as well, because you couldn't actually buy an electric car in 2005. We'd had the GM1, which had been discontinued, and we hadn't yet any new electric vehicles coming from either traditional OEMs or the new startups. I remember having a very simple question, which is, well, why are there no electric cars? Surely they are a critical ingredient to reducing our greenhouse gases. And that really started me on a journey of asking that question: what is stopping the electric car from becoming mainstream? Whilst I was doing my PhD, it became clear that some new OEMs and some traditional OEMs were also starting to explore first electric vehicles. And what was interesting is they tended to take standard technologies that existed at the time, like radial flux motors, lithium-ion batteries, and packaging them to demonstrate you could make a viable electric vehicle. On a PhD, you tend to want to investigate more a component or a material or a subsystem. And my PhD took the direction of looking into the electric motor. Of course, the electric motor has been around for more than 150 years. So I did get asked by a few academics, why are you investigating this? I would often respond, well, electric cars are new, and no one has really investigated what an electric motor needs to look like for the upcoming electric vehicle industry. A blank piece of paper approach is a very unique opportunity, and that took me down the route of axial flux machines. They had some known benefits around torque density, but also was seen as a very unproven technology.
Axial flux and radial flux were recognized as potential EV motor topologies in the 1800s. In 1821, Michael Faraday developed a primitive disc motor which already had the shape of an axial flux machine. Over the decades that followed, both of these technologies were explored. But despite the potential for weight reduction, it was the difficulty in manufacturing of the axial flux technology that limited its commercial viability, because the motor could not be made by stacking laminations as with the radial machines. The axial flux design also suffered from a number of additional problems, including poor cooling capability, key to high torque density, difficulties in controlling the axial air gaps, and a complex winding. Despite the challenges, Tim began researching the axial flux motor in combination with new materials, in the hope of finding a novel solution to these problems.
This is a great example of a radial machine. It's about 400 Newton meters. It's about 50 kilograms. It's got maybe 25, 30 kilograms of iron in it. Now, I'll compare that to an axial flux machine. Here's a motor of similar sort of torque. You can see it's similar-ish in diameter, but you'll notice very quickly it's only about a sixth of the length, so huge space saving, about 4 times the torque density. So that gives us some really interesting opportunities to package motors in new places in vehicles, reduce weight, reduce mass, and reduce cost.
The YASA axial topology and the subsequent removal of 60 to 80% of the stator's mass, removing the heavy iron yoke, and as many other metals as possible, enables up to 480 horsepower from a 24 kilogram motor that occupies significantly less space than a radial equivalent. So how did Tim solve the problems others couldn't?
There are many different types of axial flux motor, and One of the big problems with them traditionally is they need quite a lot of diameter. So if you have something of similar torque, it might be that the diameter is another 50 or 60% bigger. And that actually causes a big problem packaging axial flux motors in electric vehicles. And one of the big breakthroughs in my PhD was we actually came up with a completely new topology of axial motor called the YASA machine, yokeless and segmented armature, where the stator is broken into a number of pieces. And through a number of magnetic and thermal tricks, we were able to squeeze the diameter so they're actually pretty comparable with radial machines, making them much easier to package in vehicles. So here we've got one of our production motors, which we've cut away the front face and removed the rotor so we can see right inside the stator, which is where all the detail is happening. Now, you'll see it looks very different compared to a radial machine. First of all, we've got the stator cut into a series of segments, and we've got these direct windings around each segment. Now, there's a bit of a funny story why the motor looks like this, because during my PhD, I was very keen to use a material called SMC, soft magnetic composite. But because of press limitations, you could only make relatively small components out of this material. So by working with different axial flux topologies and this limitation on press size, stumbled upon this very interesting concept for an electric motor, which we call YASA. And we found out as we investigated this topology that it had some really significant advantages in efficiency, weight, size, and mass because of these very particular segments and the way we design them.
These savings gave YASA a unique benefit to reaching an improved efficiency goal for the automotive industry.
So of course, saving weight is one of the critical targets that the automotive industry has to make our vehicles more sustainable. Less weight means less material, less energy to make those materials, and therefore less CO2 made in manufacturing the vehicles and driving the vehicles. A big part of efficiency is making the vehicle as light as possible. And something we really are passionate about within YASA is making our subcomponents, so the motor, the gearbox, the inverter, as light as possible so that those savings then get compounded around the vehicle.
This provides an interesting sequence of knock-on effects. YASA motors offer a 5 to 10% range benefit due to their efficiency and reduced mass. Maintaining the same range could instead translate to a 5 to 10% battery size reduction, perhaps lightening the EV by 50 kilograms. But it actually grows to something bigger than that because of a mass compounding effect. Lightening the battery means you might end up losing another 50 kilograms somewhere else on the vehicle, because suddenly you need a smaller motor because the car's got lighter, and then, just as suddenly, you need smaller and lighter brakes, again increasing range. All these changes require reduced associated systems, resulting in further efficiency improvements. This compounding effect has pretty much a 1-to-1 ratio in EVs. So if a pair of YASA motors are 50 kilograms lighter, and we save maybe another 50 kilograms on the battery pack, that 100 kilogram saving turns into a 200 kilogram compound saving, which starts to get quite significant in adding further range benefit. And with the improved weight comes other benefits.
The technology has this inherent torque density advantage, meaning that we can shrink the motor by a factor of 4 whilst creating the same amount of torque. Now, this is an amazing advantage and opportunity for vehicle designers because you start to be able to think about different architectures. You can maybe package the motors concentrically with the gearbox. You can maybe put more than one on an axle. You can maybe starting to think about putting them in new places in the vehicle. So suddenly new architectures and opportunities start to open up which aren't possible with radial machines.
However, there were still many challenges facing axial flux technology that would need to be solved to scale for OEM automotive needs.
YASA span out as a business in 2009 from Oxford University. But there were two problems. Firstly, there were no electric cars. Our product had no market in 2009. And the second problem is that the technology wasn't mature enough to go into a series production electric vehicle project. One of the unforeseen challenges of industrializing a new product is there were no suppliers to make the product, and there were no machines to make the machines. So A lot of the first 5 or 6 years of YASA's journey, apart from doing demonstrator vehicles, was about proving that you could scale the technology into mass production, making the machines that could make the machine, and also helping grow the supplier base so that we have more suppliers that could feed into the axial flux motor industry.
But to do this, YASA had to build experience and knowledge by working in a range of automotive examples.
Deploying new powertrain technology in automotive is a big challenge, and we've tended to take the approach, a bit like a pyramid, to first of all aim at the really low volume niche programs, so tens of cars with Jaguar or other demonstrators going up Pikes Peaks, then stepping up into the hundreds with Koenigsegg, and then dropping into still the luxury sector with Ferraris into the thousands.
These demonstrations of the technology gave Tim and his team at YASA insights and experience which now exist in every motor YASA produces.
So we went through many iterations of the product. We improved the cooling, we improved the way it's manufactured, we made it more robust, we spun it to higher speeds. So we kept developing the product in all dimensions to make it a better, lighter, cheaper product to manufacture. We refer to those as some of the scars and the bruises of manufacturing, but we see them as a vital part of our journey in terms of making the product robust and learning how to scale it into higher volume with safe and robust processes. YASA's never been in the position to copy anyone because no one else is making a machine like this in the market.
One challenge Tim and the team needed to tackle is cooling. Similar to standard road brakes when compared to drilled and vented discs, a radial flux motor can only be driven hard so many times because as the winding gets hot, resistance increases, reducing available power. The YASA axial flux motors feature direct oil cooling to every part of the winding, which gives a unique performance proposition.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast. I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior, you know I'll always be a bit superior. Get off of me, this ain't no humble brag. I want you to hear words, you can say them back. I want you to feel free from the chains at last, and to believe in what you got, it was built to last.